Okay, welcome to the second marathon on complex numbers. You must have watched part one of this marathon. This is part two. And just continuing with the questions, it's broken up into a series of recordings, which is why you see them as separate videos. Um, so, question number 6 says the complex number 2i is defined by u. So, u equals to 2i, the complex number with modulus 1 and argument 2 over 3 pi. So, that's something important that I know the modulus and I know the argument as well, which is 2 pi over 3 is denoted by w. Find in the form x plus yi, where x and y are real numbers, the complex numbers w, the uw, and u over w. Okay, so that seems fine. If I remember my modulus argument form for the complex number, it's r cos theta plus iota r sine theta. So I can just say that the modulus is 1 and cos 2 over 3 pi plus I into 1 into sine pi over 3, sine 2 pi over 3. So let's quickly put that on a calculator. 2 pi over 3 is basically 2 into cos 2 pi over 3. So I'm just going to do that on the calculator. That gives me minus half. And sine 2 pi over 3 should give me something in root. That gives me root 3 over 2i. That's the complex number w. They've written it in the modulus argument form, which is fine. I think we should write it in the x plus yi form, and that's what I've written. Part 2 say that's w. I also need to figure out uw. So what I'm going to do is I'm going to multiply 2i with minus half plus root 3 over 2i. That gives me minus I plus root 3i squared, and that gives me minus I minus root 3. So it's supposed to be written in the form x minus yi, so x plus yi, so x root minus root 3 minus I is uw. Then I also need to calculate u over w. So let's do that. U over w would be 2i and minus half plus root 3 over 2i. So this question is about rationalization. What I'll have to do is multiply it with minus half minus root 3 over 2i and minus half minus root 3 over 2i. So it's a simple multiplication process which we've learnt in the lectures. So that gives me minus I minus root 3i in the numerator. I multiplied 2i with both the numbers. That's what I'm getting. 2 cancels out. So I'm left with minus I and minus root 3i squared basically. That's something that I missed. And in the denominator I have a square minus b square. So let's just multiply that as well. I'm just going to multiply manually. Minus half into minus half gives me 1/4, and then minus half into minus root 3 gives me plus root 3 over 4i. Then this gives me minus root 3 over 2i and plus minus 3 over 4i squared. So this cancels out. Let's see what I have here. In the denominator I have 1/4 plus 3/4, which is 1, so root 3 minus I is my final answer. So I have all three complex numbers that I was looking for. The answers match here as well, so I've done these correctly. The next task is to sketch an Argand diagram showing the points U, A, and B representing the complex numbers U, UW and U over W. Prove that UAB is an equilateral triangle. Now on the exam you'll be given an answer space like this, and you will have to plot your complex numbers. So what you are going to do is you're going to make a grid, and on the exam I would suggest that you use a ruler to do this. Don't do it approximately at times though. scale becomes skewed, and then you can't possibly see what the question is asking next. So what you should do is you should take a ruler and then sort of mark your axis. Right now I don't have a ruler on this app, so I'm going to do it manually. First I need to plot minus half plus root 3 over 2. That's w, that's the code. Okay, first thing that I need to plot is u, so I'm just going to plot 2i. So that's u. Then I also have to plot a and b. A represents uw, so uw is this minus root 3 minus I. Now minus root 3 is basically in numbers is minus 1.73, so somewhere between 1 and 2. It has to be on the negative real axis, so I'm going to mark the negative real axis here. So I'm going to say that's somewhere minus 1.73, and it needs to be minus I as well. So I'm going to put, that's A for me. And then I also need to plot B, that's root 3 and minus I, that's 1.73 and minus I. Okay, so that's approximately the same distance, so that should make an equilateral triangle sort of. In the next part, that's what the question is asking. It didn't ask me to join these complex numbers in the first part, so I'm just going to mark these and let these remain. And then what I'm going to do is I need to prove that it's an equilateral triangle. So the only thing that I need to do is I need to somehow prove that the lengths are equal in this case. There are other ways of proving it, and in the marking scheme you're going to find lots of ways. But what I'm going to do is simply, now I understand the ideas of coordinate geometry and all those things, so what I can simply do is just find distances. So this coordinate is basically 0, 2 for me. This coordinate is root 3 comma minus 1 for me, and this coordinate is minus root 3 comma minus 1 for me. So what I'm simply going to do is I'm going to calculate the distances of, let's say, ub first, and I'm going to say that minus 1 minus 2 whole square plus root 3 minus 0 whole square. So that gives me 9 plus 3. That gives me root of 12. Now let's calculate UA. Two plus 1 and 0 minus 0 plus root 3. That also gives me root of 12. Then AB. AB is simply, there's no y2 minus y1, so minus 1 plus 1 whole square, root 3 plus root 3 whole square. So that gives me again 2 root 3 and squared gives me root of 12. So if all three sides are equal, all sides equal, triangle is equilateral. Okay, that's pretty much that you need to do for the third part of the question, nothing else. So you can use your ideas of coordinate geometry, vectors, and other topics from maths to prove these questions. There's no harm in doing that. Yet you need to be careful in some questions where it's specifically talking about complex numbers because they have their own rules. Okay, let's quickly look at this question. It says the complex numbers 2 plus I is denoted by u, its complex conjugate is denoted by u star. So I know that u is 2 plus I and u star is 2 minus I. Show on a sketch of an Argand diagram with origin O the points A, B and C representing the complex numbers u, u star and u plus u star. So u plus u star is also there that I need to plot. 2 plus I plus 2 minus I, that gives me 4. Describe in geometrical terms the relationship between the 4 points O, A, B and C. So on the exam I will need to draw an accurate diagram. Right now I don't have a ruler on this, so what I'm going to do is I'm going to add a gridded page here so that I can show you exactly what is happening. It's a simple plot, so I don't really need to worry about that. The other part of complex numbers where you have more complex Argand diagrams and so on will be the part of the next marathon, so please stay tuned. Let's quickly plot this. O 2 plus I was A, and 2 minus I was B, 2 plus I. So that's A, 2 minus I is B. Okay, that's real, imaginary. And C representing U and U plus U star. So U plus U star is 4. So that's C. So I have this shape, and the first thing that I noticed about is that I've ended up with parallel lines. So what I've basically drawn is a parallelogram, but this is more of a special type of parallelogram. You can see that all sides are equal because I'm traveling the same distance. I can just see it on the grid, so it's easy to spot. So what that makes it is what I want to state in geometrical terms. So whenever it says geometrical terms, you either say that they are parallel if they're only parallel, but here specifically they're creating a rhombus. Therefore your answer should be O, A, B, C are the vertices of a rhombus. If you're not saying rhombus, you need to tell me that they are parallel, they are equal in length, and so on. Then it says express U over U star in the form x plus yi, where x and y are real numbers. So I think that's straightforward. U over U star, so 2 plus I over 2 minus I. I need to rationalize this. I'm going to multiply both the numerator and denominator by 2 plus I. I get 4 minus I squared in the denominator, and the numerator I get 3 plus 4i. So I square is -1, and the denominator I get 5, so that becomes 3 over 5 plus 4 over 5i. Now it says in the next part, by considering the argument of U over U star or otherwise, prove that this. Now this is more of a challenging question, and it relies on the rules that you've learned about the arguments. So what I'm going to say is that there was a particular rule that said that when you are trying to measure the argument of some two complex numbers that are being divided, you can simply find their arguments by saying that this is argument of U minus argument of U star. That was the rule for arguments. So on the left hand side, what I'm going to do is I'm going to write down U over U star that I just found out. It's 3 over 5 plus 4 over 5i. In here I'm going to write down 2 plus I, and here I'm going to write down 2 minus I. Now whenever you're calculating the argument of a complex number, you need to know which quadrant this is lying in. This is the first quadrant. So what I'm going to do is just going to say that the argument of this is going to be alpha, where alpha is basically tan inverse of the y coordinate divided by the x coordinate. So I get tan inverse of 4 over 3 on the left hand side. Again, when I'm calculating the argument of this is again in the first quadrant. So again, tan inverse of basically the y coordinate or the x coordinate, tan inverse of half, minus, now this is not in the first quadrant, this is in this negative quadrant 1, because it has a real and an imaginary that's negative, so it's a negative quadrant 1. For negative quadrant 1, argument of negative quadrant 1 are always minus alpha. So I'm going to say that this is basically minus tan inverse of 1 over 2. You ignore the signs when you're calculating alpha like you did in trigonometry. So that gives me tan inverse of half plus tan inverse of half. So that gives me 2 tan inverse of half. And I've proved to you that these two things are equal, and that is what the proof in the question was. So these questions are always about using the rules of modulus and arguments to prove certain expressions or equations. Moving on to the next question. Let's look at this. It says find the two square roots of the complex numbers minus 3 plus 4i, giving an answer in the form x plus yi, where x and y are real numbers. Since we've done this in the past, I would recommend that you pause the video and try to do this yourself while I also solve it once you've resumed the video. So I'm just going to do this, what I did yesterday. This question is more about comparison than anything else. So I'm going to write this as x plus yi, and then I'm going to square both sides like I did yesterday or in the previous video. X squared plus 2xyi plus y squared I squared. So x squared minus y squared plus 2xyi. So y is basically 4 over 2x, which gives me 2 over x. So x squared minus 4 over x squared equals to minus 3. Cross multiplying this gives me minus 3x squared, and I forgot to make this x power 4. So x power 4 plus 3x squared minus 4 equals to 0. Again, I'm going to factorize this like I did yesterday. So x squared plus 4 minus 1 x squared plus 4 equals to 0. So either this equals to 0 or that equals to 0. So x is plus minus 1, non-real. The question says that these need to be real numbers. X and y need to be real numbers. So x is 1. When x is 1, y is 2. When x is minus 1, y is minus 2. So the two complex numbers are 1 plus 2y and minus 1 minus 2y. The two square roots of the complex numbers. So that's my final answer then. Then part B says the complex number z is given by this. Express z in the form x plus yi, where x and y are real numbers. Very simple question. You could do this very quickly by just multiplying it with its conjugate. Minus 2 plus I plus 6i minus 3i squared. I get 1 over 5. I seem to have made a mistake somewhere. This happens when you rush through questions. Let me just check my calculations on a calculator. Minus 2 plus I plus 6i minus 3i squared gives me 1 plus 7i. Yeah. Okay, I was checking out the wrong numbers. 7i. Okay. Then it says show on a sketch of an Argand diagram with origin O representing the complex numbers this, that, and z respectively. State an equation relating the lengths of OA, OB, and OC. That let's look at the plot first. Again, I'm going to add a grid, although this is something that you will have to do on the exam. Make a grid yourself by a ruler and with a ruler and a pencil. Don't do this question without that. You're not going to get marks if the diagram is not accurate. So make sure that you always make an accurate diagram. So that's A minus 1 plus 3i B is 2 plus I, and C is Z, so 0.2 and 1.4. 0.2 and 1.4. That's a challenge. Let's see. Okay. State an equation relating the lengths of OA, OB and OC. When I'm talking about lengths, what I will certainly have to do is I will have to calculate the lengths in order for me to come up with an equation. There is no other way of thinking about this equation. Always remember to label the axes. It's important that you label them. So what I'm going to do is I'm going to calculate the length of OA, OB and OC, and let's see what the result is. So basically I'm calculating the magnitudes, or I'm calculating the modulus. So this becomes minus 1 squared plus 3 squared, that gives me root of 10. OB is basically root of 1 squared plus 2 squared, since it's 2 plus I, that gives me root of 5. And OC is basically 1/5 squared plus 7/5 squared, so that gives me 0.2 squared plus 1.4 squared gives me root of 2. So I can see that there's a relationship that when you divide root of 10 by root of 5, you get root of 2. So root of 10 was basically OA, OB, and that's OC. So I've come up with the relationship. There's no other solution to this question. That is how it's supposed to be solved. So that's the relationship. So that's part C3 that I've solved here. Moving quickly on to the next question. This is question number 9. It says the complex number Z is given by Z equals to root 3 plus I. Find the modulus and argument of Z. So modulus is simple. Modulus of Z is simply root of 3 squared plus 1 squared, that gives me root of 4, that's 2. For the argument, you calculate alpha, and in this case it's in quadrant 1, so it's going to be directly alpha. Tan inverse of 1 over root 3. Tan inverse of 1 over root 3 is pi over 6. So that's 30 degrees. Then it says the complex conjugate of Z is denoted by Z star, showing your working, expressed in the form x plus yi, where x and y are real numbers. 2Z plus Z star. So 2Z and Z star would be root 3 minus I. So that gives me 2 root 3 plus 2I plus root 3 minus I. So I get 3 root 3 plus I. That's relatively simple. That's part A. Part B says IZ star. So IZ star, complex conjugate over Z, 3 plus I. So I get root 3I minus I squared, root 3 plus I. So I get root 3I minus 1, and I'll have to rationalize this denominator because it's not going to rationalize itself. Root 3 minus I and root 3 minus I. So I get 3I minus root 3 I squared minus root 3 plus I, and in the denominator I get 3 minus I squared, so I get 3I plus root 3 minus root 3 plus I, and I get 4. In the denominator I get 4I, and that becomes I. So this answer is therefore that is what it should be. Maybe I made some mistake. Let's go back and check my calculations. I just need to be absolutely sure that I've done correct. What I've done is not correct. Just checking my calculations. Yep, there's something wrong. Let me just figure that out quickly. I root 3 minus I squared, I root 3 into root 3 gives me 3I, and that gives me minus root 3 and I squared. Oh, my bad. This should be plus 1, which is what's messing up all my calculations. So root 3 and then minus I. So I get 3I minus plus root 3 plus root 3 minus I, that gives me 2I plus 2 root 3 over 4, so that gives me I over 2 and root 3 over 2. That's the correct answer. Then it says on a sketch of an Argand diagram, show that the points this representing the complex numbers, show the points A and B representing the complex numbers Z and just IZ star, that was the one in the numerator that I messed up a little, respectively. Prove that the angle AOB is equals to pi over 6. Now this proving the angle often bothers a lot of people, so that's what my focus is on right now. So I'm going to quickly plot this and then see how I can calculate the angle. So Z is root 3 is approximately 1.73, so 1.73, and I have O in its normal position. So 1.73 and 1 would come up somewhere here, so that's A, and then I have B, which is IZ star, so that's this. 1 is on the X coordinate and root 3I is on the Y coordinate, so that's approximately here. So that's O, A and B. Now what I want to then prove to you is that the angle AOB is equals to pi over 6. So I'm trying to prove to you this angle that's in the middle of these two points. So that's theta. That's what I'm trying to prove to you. Now remember that there could be various ways of doing it. One way is through just using arguments, and that is what I'm going to do because that's the simplest one. So if I calculate the argument of A, it's going to be this, and if I calculate the argument of that, it's going to be that. So now what I can see clearly from here is that I need to subtract B's argument, A's argument from B's argument. So argument of B minus argument of A. Now if you notice, that is something that I have already done. If you notice, the numerator is basically the complex number representing B and the denominator is basically the complex number representing A. So if you remember your rules of arguments of a complex number like that is simply argument of B minus argument of A. So this question could be really short, and what I could simply do is, if I've already calculated B over A, which is this number at the end, I could just simply calculate the the argument of this complex number, and it's going to give me the correct answer. Essentially what I'm doing is I'm doing argument of b minus argument of a, but I've used this rule that says that if you have two complex numbers, you can just simply do argument of u minus argument of w instead of trying to do the entire process. So this is just going to be tan inverse of half divided by root 3 over 2. So that gives me tan inverse of root 3, 1 over root 3, which is essentially pi over 6. So that's the shorter way of doing it. What would have been the longer way? I could have used my trigonometry, calculated this length AB, use coordinates if you are unable to do it, and that's a perfectly fine way of doing it. Use the cosine rule and you can get your answer again. That would be a completely acceptable way of doing this question. Moving on to the last question for this marathon. Let's see this. It says find the roots of the equation z squared plus 2 root 3z plus 4, giving your answers in the form x plus yi, where x and y are real numbers. State okay, so if I'm just trying to find the roots, I can just use my quadratic formula, minus b plus minus b squared minus 4ac over 2a. So minus 2 root 3 plus minus, it's going to be 12 minus 16 over 2. So that gives me plus minus 2i over 2. So that gives me minus root 3 plus minus I. So those are the roots of the complex number, as you can see here. State the modulus and argument of each root. So let's take these two roots separately. Plus and minus. So the modulus is simple. It's the root of 10 and root of 10. This is in quadrant number 2, and this one is in quadrant number negative quadrant 2. So this is going to be simply pi minus alpha, like in trigonometry, and alpha is basically tan inverse of 1 over root 3, tan inverse of y over x. So tan inverse of 1 over root 3 is pi over 6, so that gives me 5 pi over 6. And this is in negative quadrant 2, so this is going to be minus pi plus alpha, so minus pi plus tan inverse of again 1 over root 3, so minus pi plus pi over 6, which is minus 5 pi over 6. I've calculated the arguments and I've calculated the modulus for each of these. Then the last part is sort of very lengthy. It says verify that each root also satisfies the equation. Now I have to go up to power 6. What I could do is I could use the binomial theorem and sort of expand the entire thing. I'm going to get 7 terms, cancel all of them out. They're going to boil down to minus 64, but time consuming process. So what I'm going to do is try to make this slightly easier by saying that z power 6 is basically squared power 3, basically a square multiplied with this itself thrice. So I'm going to say that this root minus 3 plus I squared minus root 3 plus I squared into minus root 3 plus I squared. Let's just first do one of these. So if it bothers you, you can rearrange it. You can write it as I minus 3. It doesn't bother me. So I'm going to just say that this is a squared 2ab plus b squared. So that gives me 3 minus 1 minus 2 root 3. So that gives me 2 minus 2 root 3. So all of these become 2 minus 2 root 3. And this one also becomes 2 minus 2 root 3. Now I have to multiply these 3 across. So I'm going to do it again step by step. I'm going to say that 2 minus 2 root 3, that's whole squared into 2 minus 2 root 3. Or if I remember my cubic expansion, I can also use that. But let's just quickly get through with this. So I get 16 . There should be an I here. There's an I here. All of these are with an I, which is why it's messing up my calculations. Then this shouldn't be 16. It should be 4 minus 12. That gives me minus 8. So minus 16 plus 16 root 3i minus 16 root 3i plus 48i squared. So that cancels out. Minus 16 minus 48 gives me minus 64. So that's proving the first root. I told you this is a time consuming process. There's no other way out of it. So that is that. I have to prove the other root as well. So I'm going to go again. Minus 3 minus I whole squared minus 3 minus I whole squared minus root 3 minus I whole squared. So this, remember that a lot of people make this error. This opens up with a square to ab plus b square because there are two negatives involved. So I get 3 plus 2 root 3i plus I squared. So I get 2 minus 2 root 3i and 2 plus 2 root 3i, sorry, 2 plus 2 root 3i, 2 plus 2 root 3i, 2 plus 2 root 3i. So again, this would become 2 plus 2 root 3i whole squared. So again, it sort of gives me the same answer, 4 plus 8 root 3i plus 12i squared. It's a stressful question. So minus 16 root 3i plus 16 root 3i plus 48i squared. So that gives me again minus 64. So that's the end of the first part of complex numbers. You must have noticed that I did no questions with Argand diagrams that involved loci because that's part of the next marathon. Please make sure to like and subscribe if you are watching this and want to be updated with more videos. Thank you.